scalars can be chosen according to application, your convenience. For example, set of all real numbers will be one set of scalars. So most naturally encountered set of scalars are real numbers and complex numbers. Okay? So let me start with that. So set of scalars as we defined as f in this case can be R, that is set of real numbers. C, set of complex numbers. But it does not mean that these are the only fields that we are interested in. We could have taken a set of our rational numbers or set of our integers. Okay, so they also are a good representation of fields. Or you simply take 0 and 1. Okay, every element of your vector will be either 0 or 1. So that is also a good field. So you could have chosen your scalars the way you like. But most applications we will see that either real numbers or complex numbers will be our field variables, or scalars. Scalars are either real numbers or complex numbers. Now suppose if I ask you the following question. So let me take a few examples. Okay, I'm a little bit confused here whether I should do these examples or do some more definitions and come back. Maybe I will just come back. Now, my next notion that I want to define. Once we have the vector space, we have set of vectors, operations and field and things like that. Suppose I have a vector like this. I am always trying to go from the notion that we are familiar with something which we can generalize and go to somewhat unfamiliar. Suppose I have a vector like this. Then I have another vector like this. What can I say about these two vectors? The first vector I will call it as U. Second vector I will call it as V. What can I say about these two vectors? So I can write one vector in terms of the other. Correct? I can say this V can be written as from alpha times U. Can I write like this? That means if I know U, I can pull out one scalar and multiply with this, I can get V. Correct? That means what? V depends on U. Okay? V depends on U. There is a dependence. So such a dependence is called a linear dependence. If you can obtain one vector from the other vector, we say these two are linearly dependent. But if I have a vector U like this, another vector V like this, U and V, can I write V in terms of U? I cannot obtain V from U because only a projection of this will be along this, but the other projection is in some other direction. So I cannot get V entirely from U. So if I cannot get V entirely from U, then we say these two vectors are linearly independent. Okay, so here you say U, V are linearly dependent. In this this case, you say u and v are linearly independent. Now, if you understand this notion, let me write down the formal definition of linear independence. A set of vectors v1, v2, etc. from vn are linearly independent. Linearly independent if alpha 1 v1 plus alpha 2 v2 etc. alpha n vn is equal to 0 implies alpha 1 is equal to alpha 2 is equal to alpha n is equal to 0. Otherwise, they are linearly independent. See, it is very easy to understand this definition from what we have discussed earlier. Suppose not all n alphas are 0. One alpha is non-zero, let us say. Okay. Then suppose alpha n is non-zero. When you keep this term here and take all of them on the other side, then Vn can be written as alpha 1 by alpha n into V1 plus alpha 2 by alpha n into V2, etc. So that means Vn can be obtained as a dependence of all other n minus 1 terms. So they are not. So Vn can be written as a linear combination of n minus 1 vector. That means all n are not independent. If all n have to be independent, each coefficient has to be 0. That's the only solution for this. Then only you can say they are linearly independent. That means none of these n vectors can be obtained from the rest of the vectors. Independence, that means you cannot mix them. You cannot get one from any of the other numbers. Like I showed, if two non-collinear vectors, if you have on a plane, if they are collinear, then you can get one from the other. If you have non-collinear vectors, they are not along the same line, then this cannot be obtained entirely from that. So any two non-collinear vectors in a plane are linearly independent. Any three non-coplanar vectors in space are linearly independent. You can have two vectors, and third vector is not in the same plane of these two vectors. If it is in the same plane, it can be obtained from these two vectors. But if it is out of plane, if any three non-coplanar vectors will be linearly independent vectors. Now you can say that you have a vector space. You consider any arbitrary vector and ask, can I have two vectors which are linearly independent? Maybe you can have. Can I have three vectors, four vectors, and so on? If you go on testing like this, you will reach a situation where you cannot have more than this. That means in every vector space there is a maximal set of there is an upper bound on the number of linearly independent vectors that we can construct. For example, you take set of all points on a plane. Geometrically, vectors that are lying on a plane. You can write one vector, second vector, two vectors can be linearly independent if they are not collinear. But any third vector that you put on the plane can always be represented as a linear combination of the other two non-collinear vectors. That means maximum number of linearly independent vectors that you can construct on a plane, only two. Maximum number of linearly independent vectors that you can construct in space is 3. So, in every vector space, you have maximum number. There is an upper bound on the maximum number of linearly independent vectors. But basically, when I say maximum number, that means that is the upper bound. Okay? So, we define what is called a basis of vectors. Set the maximal set of linearly independent vectors vector space is called basis. So whatever when I talked about a vector, I said a coordinate system. So in the abstract language, a coordinate system is a basis. Like x, y, z is the basis. 3 vectors, I, j, k, unit vectors is the basis. I, j on a plane is a basis. So basis essentially is the generalization of the coordinate system that I was talking. Now you know from the description or the definition of the basis that it is not unique, because I could have chosen any pair of non-collinear vectors on a plane, like the maximal set of linearly independent vectors that I can construct on a plane. So I could have chosen these two or these two or these two or these two, any two non-collinear vectors will serve as a basis. So please understand that basis is not unique. We can have infinitely many bases for a given vector space. But once you choose the basis, the components are unique to that basis. Okay? So once the basis is chosen, then the components of vector are unique. You cannot have two components for the same basis. It's like once you choose the coordinate system, components are fixed. Okay? And the number of elements of the basis is defined as the dimension of the vector space. Dimension of the vector space. Given by number of elements cardinality. Cardinality means number of elements. Cardinality. So dimensional vector space is defined as number of elements of the basis of cardinality. Okay, so we are now ready to do some examples.